As we discussed earlier, traditional computer vision systems seek to model human activities by assuming that humans operate in isolation. Typical action labels are standing versus sitting, looking right versus looking left, and so on. However, we argue that only by considering the interrelation among agents and objects in the 3D physical space, we can understand more complex behavior, forming a queue, having a meal, serving drinks. In my group, we have been working on this problem for several years now. We have introduced methods that can process a video sequence and infer the interrelations that take place among targets within a common reference 3D space. These, in turn, allow to recognize and predict complex behavior of targets. In the work by my former students Bongkun Choi, we characterize these interrelations by a probabilistic dynamical graphical model, as shown here. A1, A2, A3 are nodes describing the individual activities that each target is performing, for instance walking, sitting, standing, and are grounded to the observations O1, O2, O3. I1, 2, I1, 3, and I2, 3 capture the interactions between pairs of individual activities, for instance getting close, getting far away, walking together. And C captures the way these interactions are connected so as to form a description of the group activities, for instance meeting and greet. While graphical models are powerful tools for modeling interactions, it is often not obvious how to define an appropriate representation to ground each potential to the actual data. Interestingly, in our work by Jane and Zamir, which was awarded as the best student paper at CVPR 2016, we have demonstrated that any spatial temporal graphical model, like this one, can be mapped into a network of recursive neural networks. We call it structural RNNs. This mapping can be constructed by converting the spatial temporal graph into a suitable factor graph, whereby each factor corresponds to an edge of the original graphical model, as well as to a single RNN in the structural RNN network on the left. By using the dependencies in the factor graph, we wire these RNNs together to form the final structural RNN network. Labels are supplied top-down, and raw observations are fed bottom-up. This is a very general result that can be used to model any type of interrelations. In the context of activity understanding, this is crucial in that it allows to automatically ground interrelations among targets to any types of observations without the need of using handcrafted features. Moreover, it enables a simple forward pass through the network as compared to the loopy inference methods in graphical models. Some results obtained by our original graphical model representation are shown here. The model is able to recognize these two activities, talking and queuing, by inferring a number of interrelations such as face each other, standing after each other, standing side by side, standing in a row. So the question that comes along naturally is, how to define interrelations and rules in the first place? Do we need a domain expert to design those? For instance, an expert could tell that in general, when two people work together, they are close to each other at a certain distance range. However, this distance is function of many variables, like culture, whether the people are friends, whether they are mother and daughter, whether they are lovers, and so on. So how to define such things a priori? We are entering the space of social conventions and etiquette. Being able to model and discover such conventions automatically from data would be extremely valuable. For instance, it would be valuable in robotics for teaching a robot to understand, predict, and interact with the environment in a socially acceptable and meaningful way. To address these important questions, recently we introduced a new framework that allows regressing and predicting human intentions in a pure end-to-end fashion without specifying the number of or types of interrelations rule. approach leverages a new generalization of the LSTM, long short-term memory network, which we called social LSTM. A key property of social LSTM is that it automatically discovers the interrelations among targets as intermediate mid-level concepts. Because the interrelations are discovered and not handpicked, classification and forecasting errors decrease dramatically as shown in this plot. Here, social LSTM is used to predict human trajectories by modeling human-human interactions. Performances are measured by average displacement error. Our approach is compared against several baselines and consistently achieves superior performances. Let me show you now a few anecdotal examples that demonstrates that social LSTM is capable of successfully predicting future trajectories of targets. Here we see two targets, 1 and 2 in green, at time t. The future ground truth trajectories, that is after time t, are shown in black. These ground truth trajectories indicate that the two targets are walking toward each other and target 1 changes trajectory at some point. Trajectories are seen from the top view. The past observed trajectories, that is before time t, are shown in gray. Trajectories predicted by social LSTM are shown as a heat map. Hot colors means that the location is predicted with a high probability, whereas cold colors means that the location is predicted with low probability. Now let's examine what happens as the time goes by. At time t plus 1, target number 1 starts turning right, according to the ground truth in black, whereas social LSTM predicts a linear trajectory similarly to a simpler linear prediction baseline. However, as the video advances and the network observes the two approaching targets for a longer period, the predicted trajectory becomes much closer to the ground truth one and deviates from the simpler linear model. So thanks to the interrelation models that the social LSTM has learned in training phase, we can accurately predict the way these targets interact and avoid each other. Now a question arises. Where do we get the data from for training such a complex architectures? Existing datasets that capture target-target interactions are typically small in terms of number and types of interactions. So we introduced a new dataset that we call the Stanford Drone Dataset. This dataset captures top-view observations of various types of targets that are traversing the Stanford University campus. Examples of targets are pedestrians, bikes, skates, carts, cars. These videos are acquired by a drone that is flying over the scene at an altitude of about 60 meters. The Stanford drone dataset includes more than 100 scenes with thousands of annotated trajectories and hundreds of thousands of interactions. This dataset is the first of its kind that captures all these types of interactions at the scale and was recently presented at ECCV 2016. Interestingly, as we analyzed large volumes of such trajectories from this dataset, we found out that targets can be naturally clustered in various types of interaction types, which reflects different classes of interaction behaviors. For instance, aggressive, mild, and decided. This is illustrated in this plot, which collects the distribution of targets as function of two parameters, sigma d and sigma w. Sigma d captures the preferred personal distance that two targets keep as they get closer to each other, whereas sigma w captures the distance w at which a target reacts to avoid a collision. By running a simple clustering algorithm, we can identify 4 clusters shown in different color codes, which corresponds to 4 different interaction styles. For example, the green one corresponds to a mild behavior. Personal distance is large, and targets change their trajectories while in advance. As the box on the right-hand side shows, as target 2 approaches target 1 follows a conservative trajectory, green curve, and tends to avoid target 2 as early as possible. Another example is shown in the red box here. As target 2 approaches target 1 follows an aggressive trajectory, red curve. It tends to avoid a collision with target 2 at the very last minute. Other examples are in purple and black. Our experiments shows that by injecting these different interaction styles in our activity and prediction models, we can actually achieve much higher accuracy compared to the case where no interaction styles are used. Social LSTM and our methods for discovering patterns of social interactions is a key component of the brain of the new experimental robotics platform, which we have been developing in my lab and we have called JackRobot. JackRobot is mounted on a Segway and it is filled with sensors such as lidars, cameras, thermal. Its goal is not to just find its way through the scene or avoid obstacles, but also to be interactive, amicable, and compliant to the unwritten social rules of pedestrian traffic. For instance, it would learn what is a good personal distance, how to share resources like sidewalks, parking spots, when it is a good time for a person to take its turn, how people signal each other to coordinate movements and negotiate spontaneous activities such as forming a line. This work has generated large interest in the robotics community as well as received substantial amounts of news coverage so far, including the Financial Times, BBC News, and MIT Technology Review, to name a few. In conclusion, I hope I have convinced you about the importance of modeling the interrelation among objects and people in a 3D physical space. That is, finding methods and tools for connecting the dots among various visual cues and inferring the context of a scene. This is a crucial ingredient as we move towards building visually intelligent agents that can recognize and navigate in a complex 3D world. This is also critical if we want to have these agents to learn and adapt to the human social conventions and coexist with humans within a shared ecosystem. And with that, I would like to thank you for your attention.